Welcome to my projectbazaar.com. Let me discuss about the project Global Image Denoising. Let me discuss about the abstract of the project. Image denoising is an important image processing task, both as a process itself and as a component in other processes. Many ways to denoise an image or a set of data exist. The main properties of a good image denoising model is that it will remove noise while preserving edges. Traditionally, linear models have been used. One common approach is to use a Gaussian filter or equivalently solving the heat equation with the noisy image as input data, that is a linear second-order PDA model. For some purposes, this kind of denoising is adequate, but a drawback of the linear model is that they are able to preserve edges in a good manner. Edges which are recognized as discontinuities in the image are smeared out. One popular model for nonlinear image denoising is the total variation filter, that is DV filter. In some denoising approaches such as bilateral filter, large NLM estimate each pixel separately fusing other similar neighborhood pixels. Some other reason or state-of-the-art patch-based methods such as BM3D and Plow denoise a group of similar patches together. These patch-based methods are inherently limited in performance. Global denoising algorithm is to be proposed. It is non-local patch-based processing, where each pixel is estimated from all pixels in the image, analysis of spectral decomposition of its parameter, and computed on approximation to the spectral components using the Nystrom extension. Then the Synchron method is applied to estimate the eigen decomposition of the symmetric and double stochastic filter. To get orthogonal eigenvector, Synchron result transfer to orthogonalization procedure. This global sample-based filters approximation employed in a small fraction of the total number of pixels. Let me discuss about the flow diagram for our process. Here, input image has been taken from the dataset folder. Next, in the pre-processing step, in image pre-processing concept, pre-processing processes are required to evaluate further processing the image. In pre-processing steps, we can resize the image with a specified size. We add a noise to the image in terms of sigma value. If we increase sigma value, order noise ratio is increased, so the PSNR value gradually decreased. Here we are going to perform denoising operation, so there is a need to add noise to the image. Next, in the approximated image. In the approximated image, here Nystrom approximation has been used. The Nystrom method seeks the numerical solution of an integral equation by replacing the integral with a representative weighted measure. The continuous problem is broken into n discrete intervals. Quadrature or numerical integration determines the weights and locations of the representative points of the integral. The discrete problem to be solved is now a system of linear equation with n equation and n unknowns. The Nystrom method is an efficient technique used to speed up large-scale learning applications by generating low-rank approximation. Crucial to the performance of this technique is the assumption that the matrix can be well approximated by working exclusively with a subset of its columns. Spectral graph theoretic methods have recently shown great promise for the problem of image segmentation. However, due to the computational demands of these approaches, applications to large problems such as spatio-temporal data and high-resolution imagery have been slow to appear. The computational demands can be solved for the numerical solution of eigenfunction problems known as the Nystrom method. The application of the Nystrom method is spectral clustering, kernel ridge regression, support vector machines, kernel logistic regression, and manifold learning. Next, in the decomposed image, that is approximated images are decomposed with the help of Synchron method. The Synchron theorem states that every square matrix with positive entries can be written in a certain standard form. Then the Synchron knot algorithm can be used to balance the matrix, that is to find a diagonal scaling of SAS, that is doubly stochastic. It is known that the convergence is linear and an upper bound has been given for the rate of convergence for positive matrices. Sinhan proved that every entry-wise positive matrix can be made doubly stochastic by multiplying with two diagonal matrices. If A is n cross n matrix with strictly positive elements, then there exist diagonal matrices D1 and D2 with strictly positive diagonal elements, such that D1 D2 is doubly stochastic. The matrix D1 and D2 are unique modulo multiplying the first matrix by a positive number and dividing the second one by the same number. Here the Sinhan method is applied to estimate the eigen decomposition of the symmetric and double stochastic filter. Next, the decomposed image are get orthogonalized using orthogonalization algorithm. Orthogonalization is the process of finding a set of orthogonal vectors that span a particular subspace, formally starting with a linearly independent set of vectors in an inner product space, that is most commonly Euclidean space. Orthogonalization results in a set of orthogonal vectors that generate the same subspace as a vector sum. Every vector in the new set is orthogonal to every other vector in the new set, and the new set and the old set have the same linear span. Methods of performing orthogonalization include gram schematic process, which uses projections, Gauss-Holder transformation, which uses a reflection given rotation. Here in our process, the corresponding decomposition is not fully orthogonal. Near orthogonality between prediction and update operators leads to significant improvements in energy compaction. To get orthogonal eigenvectors, Sinhan result transfer to orthogonalization processor. Orthogonalization is the process of finding a set of orthogonal vectors that span a particular subspace. Finally, we obtain the denoised image as result. We discuss about the running procedure for our process. Select the main dot file in the current folder, right click the file and run for executing this process. This is the main window for the denoising using glide. By pressing the input image button, we can browse the input image from the dataset folder. Select any one images from this folder. Here I display the input image in the axis on plot. By selecting any one sigma values, we can add the noise into our input images. Here I selected the sigma value ranges as 2. By pressing the noise image button, we can create the noise image with the help of sigma ranges. Here I display the noise image with initial PSNR of 22.9 dB. By pressing the next button, we can move on to the glide window. Here the global denoising algorithm and also the NLM algorithm also proposed for denoising our input images. Here by pressing the glide button, we can execute the process of glide and also the existing processes NLM, that is non-local means. In the glide approach, they have been performed Nystrom method and also the Sinhan method for orthogonalization. Here we display the pre-filter using NLM operation with a PSNR of 33.10 dB. Our proposed algorithm provide the PSNR as 37.13 dB. Here I displayed the NLM and PSNR result. This is the eigenvalue which will be calculated from the glide approach. By pressing the graph button, we can estimate the PSNR and MSE value. It is mean square error and also peak signal to noise ratio for 5 iteration. So this glide and NLM approach will be repeated for 5 times. This process will take for some time. This process will take some time for executing. Here we got the PSNR plot between proposed system and also existing system. Here we got the MSE plot for proposed and existing system. X label denotes the noise level and Y label denotes the MSE values. The X label denotes the noise level and Y value denotes the PSNR value. Global image denoising has been implemented, which is a truly global denoising algorithm. PSNR value for global filter is to essentially perfect reconstruction of the noise-free image. Thank you.